So much. All right, welcome back. Today we have 3 more lectures. The last lecture will at least in part be a seminar. Today and tomorrow will be field theory. And so you remember that we started the lecture course with studying symmetry-protected topological phases. First a fermionic case, and then a bosonic case, which was a spin chain. And we're going to describe now the same thing field theoretically. Now, for the fermionic case, this amounts to 3 fermions, and there's not much to study. At least I don't think it's that interesting to cover it here. So therefore, we are going to concentrate on the bosonic case, which were spin chains. Then the next thing is that we have discussed something which was arguably topological. And topology in the context of field theory oftentimes appears as non-trivial solutions to a set of point equations, so something like instantons. These are best captured in path integral formalism. So therefore what we need to do is we need to do it in path integral formalism. In diagrams it's essentially impossible to capture these effects. Therefore, what we do now is we're going to discuss the path integral of the spin. I guess some of you have seen it. Who's seen the path integral for a spin? Only one? Okay, so it's good that I know. We will thereby introduce, or we will encounter topological terms. How far is Bash in his lecture course? Did he get to, first of all, did you see the sigma model already?
Yeah, so Bash tell us about the model in terms of path integral fermions.
Okay, very good. But he told us, told you means he like wrote it down. Yeah.
He write like path integral.
He write. Good. And did he also say something about topological terms yet or not yet?
No.
Okay, so this is going to be a little bit hand in hand. I'm trying to give you a maybe simpler manifold. I mean, you probably saw that the manifold of the sigma model is some crazy Grassmannian. I'm going to give you a simpler manifold where you can see the effect of topological terms. Okay, so this is chapter 7, topological field theories. And 7.1 is the path integral for a spin. Maybe I should ask a different question. Who's familiar with path integral formalism? Okay, this is also not that big fraction. So there is an exercise sheet which is online, and this exercise sheet is the Feynman path integral formalism to describe the particle on a ring. In particular, in the case when there's a flux threading this ring. If you're not used to path integral formalism, and also get a feeling of the topological terms, it might be helpful to look at this exercise. It's even simpler than what I'm doing here. Okay. So what we're doing is we're considering spin S. And what we need to define is the coherent states for the spin. Sort of the semi-classical, the most semi-classical states that you could have. Coherent states. So maybe you want to remind yourselves of coherent states in the case of bosons, for example. Probably most of you know this. In the case of bosons, these are the eigenstates of the annihilation operator. Bosons. It's just a side remark, but remember that there are these coherent states which are maximally classical if you want. They minimize the uncertainty. And in the case of spins, what we take is So a spin is something that is sort of a vector, right? So what we want to have is, so you see, so in the case of bosons, this is a complex number, which is essentially, so the cat has this complex number, illustrating that this is the complex number that you get upon application of the annihilation operator. And you see that bosons somehow they're going to be, well, there's something like complex, right? There's B and B dagger. Here we have something which is like a vector. So the spin, the operator of the spin is called S. Maybe I dropped the hat everywhere. And we want to have an eigenstate of the S, which is somehow a vector, so we define it as follows. When we take the N is a unit vector. N is the unit vector on the sphere. And if you project the spin operator on this direction unit vector, in this case we get S. That's the definition of the spin coherent state. Now what we will need throughout the lecture is something that at least I need to remind myself every time by opening Wikipedia to get all of the coefficients right. We need spherical coordinates. Let me remind you of those. So ER is direction perpendicular to the sphere, which is going to be the same as n, and it's going to be cos phi sine theta sine phi sine theta cos theta. We need E theta, which is essentially the theta derivative of this thing here. That's going to be cos phi cos theta sine phi cos theta. It's minus sine theta. And we need E phi, which is just minus sine phi. It's just spherical coordinates. So we take the spherical coordinates with n being the direction on the sphere. N is pointing somewhere on the sphere. Okay, so and let's now explicitly construct such a state. Do I need to say that? Sorry, maybe I say this explicitly also. Phi is between 0 and 2 pi, and theta is between 0 and pi. So let's construct such a state explicitly and start with spin 1/2 to get a feeling for it. So, example. S equals 1/2. So we can explicitly construct this. So then therefore, of course, that means that S, in this case, is Pauli matrix. And the state that we get is actually this one. N is going to be 1 plus n sigma half acting on some state that we choose 1, 0. So if you use this basis that we chose here, so this is a basis independent statement. But if you choose this basis here, then it looks like this. E to the minus I phi half cos theta half e to the I phi half sine theta half. And we call this complex two-vector Z. So what we use here also is the normalization. Actually, we use the normalization even with the phase. So here we use n equals. Here we use n minus I half divided by cos. Sorry, it's going to be a bit dry in the beginning. I have to give you lots of definitions to get there. Okay. So do you see that this guy is that this state has this property? I mean, the main point is that when you do n sigma, this is some direction of sigma, right? I mean, sigma is a vector, and we choose one direction. Let's say we choose the x direction. Then what would be here is 1 plus sigma x. And of course, if you have, or maybe even easier, 1 plus sigma z. 1 plus sigma z, that's just the projected, right? And if you act with sigma z on this one, well, you get 1 in the basis sigma z, right? We're looking at sigma z. And this is the rotated version of this. It's just in any direction on the sphere, not only in the z direction, this is the corresponding protector, and that's why when you act with n times s on it, you get s. Okay, step 1. Then, what's important is that we take the expectation value of any function of s with respect to this state. We get just f of and half. It's a state if, yeah, this is normalized, so we get essentially this out. So how do we see this? To which is the same argumentation as what I just told you. So we're going to Taylor expand this thing here. This function of operator s is defined by a Taylor expansion, and all you need to know is essentially this thing here, n s n, right? But that is going to contain, so we can write that like this, up to this number here, 1, 0, and then we have 1 plus n dot sigma, half, and here we have s, here 1 plus n dot sigma, half, and here 0. That part is not important. The important is this here. And it's useful to expand s in the direction which is parallel to n, and two directions which are orthogonal to n. The direction that is parallel to n is the part where we have n dot sigma and it commutes with this protector. So we can pass the protector across and nothing happens. But for the contributions of s which are perpendicular to n, we will have anti-commutation with sigma, with this n dot sigma. We bring it across and we have 1 plus n dot sigma times 1 minus n dot sigma, which is 0. So I write here only component parallel to n survives. Alright, then we want to know the overlap. We need to calculate the overlap of this thing with slightly different coherent state. So n prime overlap. What's this? Okay, so I'm not going to do it explicitly, but all of this, of course, for s equals half, right? It's going to be e to the I some phase, and we will see in a second what this phase, the leading parts of this phase are. Square root 1 plus n prime. So you can actually calculate the absolute value squared of this overlap, and relatively quickly find this part here. And from this here, what we need is essentially, and this is actually the more important bit for all that comes. What we need here is only the leading term, and the leading term comes from these fellows here, this and this. So e to the I alpha of n prime is going to be, just expand this, 1 minus I cos theta phi prime minus phi half plus dot dot dot. This is an expansion in the case when n and n prime are not very far from each other. So if you want, it's an expansion in small phi prime minus phi and small theta prime minus theta. And where does this come from? So when you take the overlap of this to this here, and you have slightly different phi and phi primes, and obviously you see that you get this, I mean, from this term with the one with the primes, you get already the difference of phi minus phi prime. Right? And here the same thing, you get also the distance of phi minus phi prime, but with a different sign in the exponent. So what we essentially used here, this trigonometric identity, the leading order, which is this cos squared theta half minus sine squared theta half plus cos theta. That's where this cos theta comes from. This cos theta comes from. Yeah, and this here is just the expansion of these exponentials. That's the part that is going to be useful for later. I mean, that's something that's relevant for the derivation of the path integral.
I have some questions.
Yes.
Wait, why is n prime close here? I mean,
This is just an assumption. Here is an assumption.
but the first equation holds generally.
This is generally true, but I didn't tell you what alpha is.
Okay, and this is for spin half.
This is all for spin half. Everything that you see here is for spin half.
Okay, and then above their expectation value fs, above one line. Yeah. So on the left you have a number, and on the right you have an operator.
No, that's this hat means unit vector.
Oh, sorry, right.
Sorry, that's confusing.
So,
But I didn't put hats on operators, so
yeah. So,
operators have no hat, and hats means unit vector.
so for spin half, the coherent state is literally just like plus one eigenvector of the s dot n operator.
That's right. Plus, in the case of spin half, it's 1/2 eigenvector. Yeah. Okay. And then what we also need is we need the partition of unity. So the completeness relation, if you wish. And maybe for completeness, I put it here. It's not very long. So we have everything on one backboard. Last bit is partition of unity is 2 integral dn on the sphere n. So this is tetra n tetra is 1. So if you wish, I can show you extra steps, but essentially what you do is you plug in this definition here, this one. So in terms of the z's here, and then you integrate over the sphere using the standard method for spherical coordinates. So it's d phi and then d cos theta. And you will see that this is the right thing. This is a normalized measure. It's normalized such that it's normalized to 1. So if you take the integral over 1, you get 1. All right. And now we can switch to more general S. General S. And what we're using is what we just learned for spin 1/2. So what we're doing essentially is, so the general S looks like this. We have N, which is Z alpha 1, Z alpha 2, all the way to alpha 2s. And then we take alpha 1 and alpha 2s. So what is this thing? So Z, all of these Z's, they have 2 indices, so this alpha has 2 indices, up and down. This here is a product, I mean this is living in the Hilbert space of 2s spin 1/2. And what we're taking from the Hilbert space of the 2s spin 1/2, we're only taking the symmetric combination of it. Obviously this here is completely symmetric. So what you take here is also only the symmetric combination thereof. What you're essentially doing is something that I think we briefly discussed before as well, in the context of the solution of the AKLT chain. We are embedding the problem into sort of a Hund's rule constrained Hilbert space of spin 1/2s. So if you think in a Hund's rule dominated atom, how do you get a spin 3/2? You get it by taking 3 spin 1/2s on top of each other, and that's exactly what we're doing here. Yes.
Why is it obvious that this is symmetric?
So what we're doing, okay, so this here is completely symmetrized, the definition, but you also see that this here, since all of the z's are the same, I can exchange index. If you think of this here as an arbitrary tensor, if you think of this as an arbitrary tensor alpha 1 to alpha 2s, if I exchange two of these indices, since any of those has the same z in it, nothing is happening.
But the z is just.
It's just this thing up there. So it's just this thing up there. So we can. So it's again, if you wish, it's expressed. So it's expressed explicitly in the coordinates that we've chosen, phi and theta. So each z is a function of phi and theta. Right? There's two entries. Each of those is a function of phi and theta. So this n here is a function of phi and theta. This is entering through all of these z's here. All of the z's are functions of phi and theta.
But is it the representation in Q space or is it a cat?
So z is okay. Maybe you don't like that. I just jump from here in abstract cat to things which are two-dimensional spinors. Is that what you don't like? I don't know. Yeah, I just do this famous thing. Yeah. But I think it makes sense now.
Yeah. Okay.
So for a spin 1/2, the Hilbert space is essentially a two-dimensional complex vector, which is not nice. Okay, so does anybody know what the Majorana representation is for spin S? It's exactly this, yeah. So you know what the block sphere is, right? Everyone knows what the block sphere is. Essentially it's what's the z up there. So to illustrate a state, a common state, you draw it on a sphere, right? And then there is something like the Majorana representation, which is exactly this. So you draw two dots, and you take the symmetric version of it. So there are various things. You can, for example, there's a situation when you put them on top of each other, then it's really going in the same direction, and you have a spin 1 in this situation. It occurs, I personally have first encountered this Majorana representation in the context of spinor Bose-Einstein condensate. So when you have spin 1 bosons which condense, then this is the representation of the boson. Anyways, there's a generalization of the block sphere, and that's called Majorana representation, and there's nothing but this illustrated graphically. So if you hear Majorana representation, then you know about it. Okay, good. So now what about the identities that we had there? The important ones are the following. So the identities, first identity is this expectation value, n f of s n. Now what you have to do essentially is, maybe I do this here explicitly so you see what's happening. So you add all of these z's here. So you have z alpha 1 star all the way to z alpha 2s star, z alpha 1 prime all the way to z alpha 2s prime. So we have this, alpha 1 alpha 2s. Here we have alpha 1 prime, alpha 2s prime. So far all that I've done is I've expressed this n with these alpha primes, and this n with these alphas, and here there's a star because it's a ra rather than ket. And here what we do is, as I just said, we're embedding this large spin S into a Hilbert space of 2s spin 1/2. So what we're doing is this sigma I half. So we're representing. So this n here is this. This n here is this. and the S has been replaced with this. And now effectively what you can do is you can use this expression up there multiple times. And what you end up with is that you just get, since you have the same Z everywhere, you just get F of S times. And so here, this F in the sum, let's just take, first of all, let's take something which is linear in this thing. Then the sum sort of falls apart, and the ith sigma only acts on the ith alpha, and then you can just use the formula above essentially, and then you do this n times, and that's how you get this. Sorry, do it 2s times, so you get this s. Very similarly,
Sorry,
yes.
so the alphas are plus minus half, or?
Yeah, that's right, or plus minus 1, or up and down, whatever you like best.
So when you say z to the alpha 1, I mean is the 0 and 1, or to the minus half and plus half? Like, you take all
This here means, this means I'm contracting, this is Einstein convention. I'm contracting this alpha 1 prime with this alpha 1 prime.
Sorry.
So, yeah, so I take the up component when I have up here, and then take the down component when I have down here. Is there another question?
So what's the boundary?
What's the what?
What's the upper boundary?
This one? You can read this. That's the question.
Yes.
Little less. Yeah.
Could you repeat why we have 2s?
Because we want to make a spin S. So, how do I make a spin 1, for example? I take two spin 1/2s on top of each other. So, oh, sorry. Did I do this right? So, for spin 1, let's say S equals 1. So, I need to take two spins. Sum goes from 1 to 2. If I take spin equals 3/2, I need to take 3 spins stacked on top of each other. Okay, so the overlap is essentially just taking this here multiple times. So what we do then is this, the overlap is e to the I 2s alpha of n and n prime. It's the same alpha as there, it's generally something antisymmetric, and in particular the leading terms of those, times 1 plus n times n prime half to the s. Everything follows from this construction. You can just plug it in. And similarly, partition of unity is 1 equals 2s plus 1 integral over the 2 sphere n. So maybe I should define this once properly so you see what this integral is. So, side remark, integral dn over the 2 sphere means 1 over 4 pi integral d phi 0 to pi, and now you can write it either as integral d cos theta minus 1 to 1, or you can write it as integral d theta sin theta. Okay. Yeah. That's it. Just some, so far it was just some definitions. Path integral? Okay, let's go to the path integral, 7.1.2. Oh, sorry, this was 7.1.1 actually. Path integral for a spin. Sorry, I forgot. So how many of you know about path integrals in general? So just a very basic idea behind it is the following. You have quantum mechanics, which is the physics of interference, if you wish. You can think about the double slit experiment and know probability to get here, you have to sum over all these amplitudes here in this sphere. So for a double slit, you have these two amplitudes. And when you have a triple slit, you have maybe one more amplitude, and when you have a quadruple slit, you have even more. And as I do more and more holes into my screen, I get more and more of those paths. And the path integral is essentially summing over all the paths. In particular, in the situation when you remove the screen entirely, just integrate over. That's what path integral formalism is. And we're doing this now for a spin. And we're deriving this very similarly to the path integral of, if you want, well, on the one hand, this is a path integral for a single particle, so it's similarly more similar to the Feynman path integral of quantum mechanics. But on the other hand, it's for this weird coherent state, so it's a little bit reminiscent of what you know, those of you who know, for the path integral in many body physics, which is the path integral of coherent states of either Feynman's or bosons. So what we're doing is we're looking at the partition sum, which is trace e to the minus beta, and we have some Hamiltonian of s. And what we're doing, and again, if you've never seen this, it's good to do the exercise. What we're doing is we're going to, so what we have here is this beta, and we're going to sort of split this in slices. So this here, which is a single exponential, we write this product of n exponentials, slicing what we will call imaginary time into this. So what we will do is we will make like a bunch of slices here, 10 of those. And at each of those, delicious, yes? Was it? No? And at each of those, we insert a unity everywhere. The unity that we insert is this one. So what we then get is limit of n goes to infinity. And now we have this n partitions of unity, 2s plus 1 I. And then we have product of I goes 1 to n, and I plus 1, e to the minus delta tau, h of s operator. So what we're doing is, when we do such a partition of unity, for example, at this point here, this point, we insert n1, n1. At this point, we insert, right now, I'm going in the wrong direction now. It looks like I'm going in the wrong direction. I start from here. Here I call it n1, n1. And here I have something like the n2, n2, and in between here, between here and here, I have e to the minus, and now I'm only a part of this guy. I split this in n bits, e to the beta over n h of s. This beta over n is what I call delta tau. And I will send n to infinity, making the smaller and smaller. Then I have more and more integration for levels. So I have this overlap of, in this case, n2, so this expectation of n2, then this exponential is this thing here, and then the n1. And this repeatedly. Okay? Yes?
Why do we need the limit
So that's to get it, well, I mean, so the goal is to get a field theory, which is going to be dependent on time, in this case imaginary time, continuously. And that's why we take this n goes to infinity. So it's actually, okay, I should say, this whole thing is a mathematical trick to derive a partition sum, to represent the partition sum in terms of this path integral. Path integral being the integral of all possible paths. These steps that I'm showing, they are quite standard. You find them in many textbooks. They are not super mathematically rigorous because what we're doing at some point is we assume certain continuity. I think very mathematically inclined physicists would prefer to just write down the path integral as what the final result is and check that whatever you evaluate with the path integral in terms of the field theory is the same as the partition sum that you have written. But it's a good motivation. I like it. It's standard. Okay, so now, so what we've used now so far was this partition of unity. And now the trick of the path integral is that you sort of essentially you expand this, and then we exponentiate it. So what you do, you expand this here as 1 minus delta tau to s. Then you take the expectation value, and then you re-exponentiate. So that means that the whole thing here is going to be exponent of I should probably write this as log of n plus 1 I, and then essentially what we have here is minus delta tau h of, sorry, it's 1 plus log plus this minus delta tau h of. And now here we can evaluate this, and essentially we assume now, and this is already this continuity assumption that this ni, at the time ni, and at the time ni plus 1, the vector has only rotated very slightly. So that essentially it doesn't matter whether I take ni or ni plus 1 here, anyway. While here, what we will use is this thing. So maybe I first write things out and then I will evaluate this overlap. So formally this thing becomes in the limit, this becomes integral, and then this measure in the limit is denoted with curly n, curly d, n exponent of minus integral d tau 0 to beta n d tau n plus h of, oh sorry, the s n. And these are now tau dependent. So this discrete index I, which I used to define the tau, becomes the continuous unit. Everything becomes a function of tau. So this n here is a function of tau, this is a function of tau, everything is a function of tau. So again, if you've never seen path integral, I recommend the exercise, and you can find it in any textbook. In quantum mechanics in part, for sure, also in textbooks on quantum inequality theory. Okay. I wanted to go to the position to discuss this here. What is this thing here? So for those of you who have seen this before, in the case of bosons, where do I put this best? In green, I put on top what you might remember from the situation, same situation, function for bosons. What you get there is something like psi bar d tau of psi, right? Very similar. In Pierce's book, his following book, this is even called the Berry phase contribution. We will see today why it's called the Berry phase contribution. Okay. What do I want to erase? You can erase this one. Oh, I still need this. Okay, let's evaluate this term here. So essentially what we need is we have this here, right? Which is coming from here. So let's see what we have. We have explicitly n of tau plus delta half. Maybe it's n of tau, n of tau minus tau. This is the continuum version of this expression. So we can now use this expression here. N prime is the n of tau minus delta tau, and n is the n of tau. So if you wish, you can write this. Well, we can just use this. We can just use this expression here. So I write it out. E to the I to S alpha of n of tau minus delta tau. And then we here the square root 1 plus n of tau minus delta tau over 2. Actually, more generally for arbitrary s, it's just this is to power s. You can actually see that for small delta tau, this guy here will be 1 plus order delta tau squared. We will drop order delta tau. We will only keep leading order delta tau. So leading order delta tau, we get everything from here. So this is going to be approximately 1 plus, so we can expand it small delta tau, I to S alpha of n of tau minus delta tau. And we can take the, oh no, I erased the alpha. Too bad. So we had this expression in terms of phi minus phi prime, which I'm going to copy again. The whole thing is going to be 1 plus I to S. Actually, I can write down explicitly the whole thing. Minus I to S cosine of theta of tau. And then we get here phi prime minus phi, which in our case means phi of tau minus delta tau minus phi of tau half. So what we get here is 1 1 minus I to S. I expand this here plus delta tau cos theta phi dot half. So let me emphasize again what is done using this process.
Sorry, there is no
Yes, yes.
contribution from theta to from the derivative of theta.
Can you repeat?
There is no contribution from time derivative of theta.
That's right. That's right. And the reason is that, so I discussed before this, I erased this alpha unfortunately, but the alpha contribution has the leading contribution in small distance between theta and theta prime and phi prime was only the phi minus phi prime part. This is something maybe to check. The theta dot part would come with a delta tau squared. And let me emphasize again what happens actually here. So we have now seen that this part here gives us something proportional to delta tau. We have here delta tau. And this product here becomes the product of, in the exponent becomes the sum over I with this delta tau. That is interpreted as a Riemann integral as n goes to infinity. And then this is where this integral comes from. So let me summarize what we got. In total. S with a spin. So we write Z as integral dn e to the minus S, where S is the Euclidean classical action. S is integral d tau. Maybe actually even write S into this. So S is S of H plus S subscript WZ, so explain in a second. SH is the part that we have here, just coming from the Hamiltonian. So it's just d tau from 0 to beta, H of Sn. This is just copied from here, or if you wish from here. SWZ is minus IS integral d tau from 0 to beta cos theta phi naught. That's coming from here, right? So we have the factor of half cancels the factor of 2. And then what we have here is IS cos theta phi naught. And there is one more thing. When you insert these units everywhere, and the last one is inserting a unit essentially. Well, what you do essentially is you evaluate this trace using an insertion unity. So there is one more unity that you insert 0 and theta at the same time. So when you have these particles for bosonic arrivals, such as these spins, there is a condition on it, a boundary condition, that n at position time equals 0 equals n at time equals beta, imaginary time equals beta. Okay. Let me now write out this SWZ in one other way. Now, 0 to beta. And this way is going to be n dot times A. A is also A of n. A of n. A has the form 1 minus cos theta over sine theta minus sin theta cos theta 0. This is defined. I've not done anything at the moment. I've just written this thing out. I can take n dot, just taking the dot of this thing here, and I want to have the contribution of it, which is actually proportional to E phi. So that's what I get from here. I get phi dot minus sine and here plus cos phi. And then what I've divided out is the sine theta part underneath. This is nothing but rewriting the whole thing. But it's somewhat suggestive because this A is a vector potential, can be interpreted as a vector potential on a sphere corresponding to what we have is a sphere. So our spin is described by the motion of the spin as a unit vector, which is nothing but a particle on a sphere, right? So you just think of the point of the arrow, that's just the position of your particle, and it runs around on the sphere. And what we found, in addition to just the kinetic part of this, we found that there is an extra term, which is this here, and it corresponds to a vector potential, which is nothing but a monopole inside the sphere. Monopole of strength, and I think it's something like 4 pi times s. Let me check. Yeah, one can say it also differently. One can say monopole of charge of strength 4 pi, and here we have our, so this is the monopole. And n describes inside the sphere. N describes particle of charge S. One can of course also reverse this. One can say it's charge 1 and monopole of strength 4 pi s. And so what we've done is we've mapped this problem of the spin. So far I didn't tell you what the Hamiltonian could be, but we have a Hamiltonian for the spin problem. And we've mapped it onto a problem which is the motion of a particle on a closed manifold, which is a sphere. And moreover, there is an extra term which, depending on the spin representation that you have, corresponds to some magnetic field that is part of the field. Okay, this is the sigma model. Because there is a nonlinear constraint, the nonlinear sigma model, there is a nonlinear constraint on this n, and this n is a unit vector, so n squared is 1. Yes?
Why can we also why does it
So what you can do is you can, okay. Maybe first the motivation of how this appears. So where you see that this could be a vector potential. When you, I can write it. let's do first usual particle. So you have a Hamiltonian of this type. Right, so this here gets you an action of the form x dot squared mx dot squared over 2 minus d of x. Right? This is just a classical Lagrangian corresponding to this Hamiltonian. What we've done, of course, what happened is that this p became something like the x dot by means of the Lagrangian transform. It's now added vector potentials. What you get actually is you have this. What this here actually is something of this form. It's still p squared over 2m. So without the vector potential, it's still this p squared over 2m plus I p x dot plus d of x. That's what you get when you do the Feynman particle formulas before the particle. Just a regular quantum particle without constraint, without living on a sphere. Now I would like to do the same thing with this A. Maybe I should also say that once I integrate over P, it's just a Gaussian integral, I get back to this mx dot squared half. So once you do integral over P, integral over P, you end up where it just was, x dot squared, mx dot squared half plus d of x. That's just because this is a Gaussian. Next, I want to include this A. So when I include this A, I do it here. And now prior to integrating, I will be shifting, I shift this P by A. I shift this P by A, so I don't do anything except for shifting it. It becomes P squared over 2m plus I, so P goes to P plus A, x dot plus d of x. And now I integrate over to P. So then I get m x dot squared half into the term, of course, plus I a x dot plus d of x. Okay. And now you see that this term here is a x dot is the same thing as this one. So you can identify this as a vector potential. So if you wish, you can think of this here as doing a calculation of this one in three-dimensional space and enforcing a v of x so strongly that it lives only in the unit sphere. So a v of x that has this form. Right? So you can take this derivation here, the standard derivation a la Feynman, and you take a v of r. Only depends on the radial coordinate in 3 dimensions, which looks like this. So that you only put everything into these levels, which are in the lowest level, sitting inside this one at 1, r equals 1. And then, same thing, you end up here, and you can identify this with the vector potential. You might have noticed that what I didn't tell you what this h of Sn is, but this here looks like a potential on the sphere. So for example, if I switch on a magnetic field, it will prefer maybe the north pole over the south pole on the sphere. But I did not include anything of the type n dot squared. Because I didn't allow in the Hamiltonian to get something which has the kinetic instant like p squared, and I only had something in Hamiltonian, my original Hamiltonian. It was only sort of position dependent. I didn't have anything which was sort of I don't have anything which was p squared like. But in principle, one may add to this term, to this Hamiltonian here, an extra kinetic term of this type. Then dot squared over some energy J. It's in principle possible. It's an energy because this here is 2 time derivatives. This is 1 time measure, so this is 1 over time. So I have to put energy in the denominator. So in the case S equals 0, forget about this term. This here, which is something like the kinetic term of this time period, just describes the kinetics of a particle running around on the sphere. And now we have supplemented this with this vector potential. Particle running around on the sphere is nothing but, the eigens, if you go back to Hamiltonian formalism, it's nothing but L squared is the Hamiltonian. J times L squared. So the lowest energy state usually, so where do I write this? So I'm still giving you sort of a little bit of folklore behind all of this. And we continue with the more strict things. So if you have S, this just as that corresponds to, now really not interpreted as a spin, but interpreted as a particle on a sphere. This is nothing but a Hamiltonian of the type J times L squared for the particle on the sphere. So its eigenvalues E are J, L times L plus 1, right? So the function of L, you have 1 level at 0 here, you have 3 levels at 1, etc. Right? 5 here, blah blah blah. The second. What this guy does here, the monopole inside your sphere changes the quantization condition of the particle on the sphere. In fact, what you have to do is essentially it changes the boundary condition for the particle. And thereby it changes also the quantization. So if I add here, if I have S equals tau and dot squared over J plus SWZ, let's say S equals a half. Then this becomes a more complicated version of this here, because it knows about the vector potential, H twiddle of A. I will not write it out specifically because I don't remember it by heart. But what you get then is you get 2 levels, the lowest energy state is 0, has 2 levels, and it's at L equals a half. And then you have 4 levels at L equals 3 halves, etc. And the energy up here is J, so the energy difference here is also J. It's all order J. J, this is something else J. So what I'm trying to say is that such a term here with a vector potential, by changing, it's just a flux inside the whole sphere, but it changes the quantization condition, and thereby makes something that has only a non-determinate ground state to something that has a determinate ground state, if S is half integer. We chose a situation where this term is absent. So far, my derivation was the situation where this term is absent, corresponding to J is infinity, which means that I've pushed up all of these states here. So for example, for S equals 0, I have just a single state. That's it. It's obviously S equals 0 is not even a split, right? For S equals a half, I push up this state all the way to infinity. I only keep this two-fifth, which is indeed my spin 1/2 particle. This is another way of seeing that this Hamiltonian, this action is equivalent to this Hamiltonian of a spin S particle. If you don't like this trotter, this is called trotterization, this discrete time inclusion. If you don't like it, you should just solve the partition sum and you will find this. Okay, so what does this all have to do with, so far I spoke about magnetic fields, etc., but I didn't really speak about topology, so I would like to speak about topology now. what's this SWZ doing? Okay, so first of all, we should remind ourselves that what we have is this situation where we have a mapping from the stretch from 0 to beta, but identifying 0 and beta essentially. We have a map from this is my time. So time, this is 0 and beta is the same, right? And this is time, Euclidean time. Or sometimes also called imaginary time. We map this here to the sphere. So that's nothing but what we're doing when we're replacing tau by n of tau. So we start somewhere on the sphere. This is at time equals 0. And then at time equals a little bit more than 0, we have maybe a slightly different point on the sphere. This n of tau takes a slightly different point. So if I trace this circle here, I will trace on the sphere, I will trace a certain loop. You can see this integral here, with this d tau and dot. You can see this as, I think it's called a line integral in English, like an integral along a contour of this type. Integral dn gamma, where gamma is this specific contour there, times a. The contour is this blue thing there, right? And the contour is actually nothing but the boundary of this area. Boundary of the red area. Sorry, there are not two different A's, but one of them has no vector. That's area. Or maybe should I call it S? You're very confused with this A? Okay, I can call it S. Okay, so now we use slopes in, oh sorry, I forgot the I. I and I forgot the I. Now we use slopes. So what we get then is that we can integrate over the whole area. I integral d2 s. Oh, I just d2 s. And then we have here R, which is same as n dot curve A. And the ER is the same as n. I already told you it's a model, I mean, I didn't show it to you, but you can take a look at this. So all that you get is, you get the you get the area enclosed of I times integral, oh sorry, this is integral I times S, area of S. So the integral here, this integral was originally defined such that the integral of the whole sphere is 4 pi, so everything was in units of everything is in units of this was in units of the sphere, the volume of the surface of the sphere. Here we get extra 4 pi. You will see in a second what the units are that we really use here. But if you want, if the whole thing is covered, so maybe I write it like this. So S here is only a fraction. This is the same S. There's only a power vector sphere. Normalization is such that area of whole sphere. Oh, that's the standard normalization. It's 4 pi. So it's just so essentially what I'm saying is that this particle that is running around here, this S Bezzomino, it just measures the solid angle that is inverse. Now I told you what this W means. It measures the solid angle which is enclosed. And that's not a surprise. It's a charged particle which is doing a loop, and there's a flux coming through it. So it's measuring the flux enclosed. Yeah, so now I said it. This stands for Bezzomino. Bez and Zomino. To sort of study these terms. First, this is maybe late 80s or so. Maybe early 80s. Okay. Good? Yeah.
What the S, so the screen S come from?
This is because I forgot it all the time. So it was present here, and I forgot it here, along with the ion, I forgot it here, I forgot it here. Yes. Thank you. Now there is a problem, because I didn't tell you what is in and what is out. So this guy here is enclosing this red area, but you could equally say on the sphere, it might actually be enclosing this green area. All the rest, who told you what's inside and what's outside? So therefore, one could equally calculate, so this is sort of the S Bezzomino calculated with the red. Yeah, okay, it's obvious from here, right? But one could equally calculate it with the green area. And the partition sum should not change depending on whether you choose the red or the green area that's inside the loop. So therefore, we need to require that the Bezzomino evaluated with red minus the Bezzomino evaluated with green so the difference between calculating everything with the red area or with the green area, this difference shouldn't matter for the partition sum, since in the partition sum the action enters as e to the minus s. We have to require that this difference is at most 2 pi I times an integer. So maybe I should put element. Then, as you calculate the green, the area that's enclosed in green, you notice that there is sort of a different, so when you do Stokes, there's different orientation, because in one case you're going clockwise, so in the red case you're going counterclockwise around the area, in the green case you're going clockwise around the area. This gives actually, this sort of cancels this minus sign, so what you actually get, the difference between the two here is IS integral d through s of the whole sphere, n dot curl A, and I already told you what that is. So this is IS times, now the area is at full 4 pi.
Why is the difference of the S relevant for the instrument?
So what do you want? So there, I told you that there is some sort of ambiguity in calculating this. this ambiguity should not have physical consequences. The partition sum contains, the partition sum is physical, you can calculate something with it like specific key or whatever. In the partition sum, the S enters in the exponent. So whether I take the partition sum with the red or with the green should make a difference. So taking the difference of the two should have no impact. That's what I think. The difference between the two is, if you wish, it's like, I want to, you know, had I taken it in the green, what would I have gotten, right? So that's what I'm trying to subtract from. I'm trying to find out.
Okay, so you need the minus sign to replicate the plus sign and
Well, I need to make sure that whichever prescription I take does not have physical consequences. So that's why I'm taking the difference between the two. I want this difference to have essentially no impact. But no impact doesn't mean 0, it means in this case 2 pi I. So, imagine that I've never heard about spins and representations of the rotation group. These arguments tell you that there is only spin 1 and spin 1/2. Because what I tell you is that, well, we have this effective particle description of a spin. And the only way to make this consistent is if 4 pi s is, or if you want 2s, is element of C. Or differently said, from the Vesumino theory, it follows that S equals 1/2, so 0, 1/2, 1, 3.5, etc. But whatever, 5/4 is not allowed. There are topological arguments why spin has to be 1/2, 1, 3.5, etc. Yeah, so let me digest this a little bit.
But didn't you think in the beginning already that it was multiple?
So, what I'm trying to say is, imagine I did not derive this, well, okay. You say that the explicit construction that I did was, of course, assuming that it's stack spin 1/2, so spin 1/2 was there. What I'm trying to say is that imagine, I never told you about this, and I just gave you this action. And from this action, you can also infer that spin is quantized to 0, 1/2, 1, etc. This is sort of similar to my argumentation that maybe you don't like this factorization and you just say make a partition sum and then you just compare. So there are sort of two different ways of describing this. And also out of this one, I mean, we all learned at some point that representations of spin can only be half integer or integer. But there's another way of seeing this, and this is a topological way, based on this path impulse. Okay.
And this is completely independent of H, except.
Yeah, I didn't say anything about H. H will, I mean, at this point, so this H here can only give you something like polarization of the field or something like that. So something like B times S or something, which would be B times N, and we're trying to point the N in a certain direction. It's also independent of this kinetic term, which I've sort of added by hand in the end. This is a purely topological aspect of the theory. So that's actually that's sort of the strength of all of this topology business, right? Because it's independent on details of, no, this is non-universal, this has a J in it, which is some energy scale, something. But all of this here is universal. You see, this S here is mentioned as something. So it has no information about microscopic details, it's just topological and very robust. Okay, so let me summarize topological terms that are present in, you can find in nature, or at least in our description of nature. Summary of topological terms. there will be 3 categories. I'm not sure if I will discuss all 3 of them. Definitely in my course, we will discuss only 2 out of the 3 categories, and Pasha might discuss also the third one. The first type is Versumino, which we just discussed. Versumino. That's of the types we just saw it. And what it more generally requires is that imagine you have a d-dimensional field theory for d-dimensional space-time. To get a non-trivial Versumino term, require the plus 1 of the manifold where the field theory lives to be zero. So the field theory is something like a mapping. Let's call it still M for simplicity. It's a mapping of space and time to n of x and down. And I call the manifold where this thing lives M. So in our case, M is a 2 sphere. In the exercise, M is a 1 sphere. But then the logic is similar to this one. In any case, even if you go to higher dimensions, you will always find the Versumino term which has this form, S, Versumino, sometimes also written, sometimes also Novikov, I, 2 pi k, it's called this gamma of, in this notation, n. And this gamma measures, well, maybe not have time to discuss all of this thing to write it down, but gamma measures this hypersolid angle, so here it measures the solid angle. In higher dimensions, I call it the hypersolid angle, measures hyper or solid hyper angle, hypersolid angle. And then there is again a consistency requirement. There's a consistency requirement very similar to this one, which imposes consistency, K in Z. So for those of you who know a little bit of conformal field theory, you might know SU2 level K and the corresponding Casimir algebra. This is the level of the Casimir algebra that would enter if you were to write down this field theory in terms of the Lagrange formula. You would get such a Versumino term, and the K would be just the level of the Casimir. Okay.
So what do you mean exactly? Pi equals 1?
This is the homotopy group. This is the d plus first homotopy group of M, and that's a PC. So that means that here, this is a 1 sphere, this is a 2 sphere. The homotopy group is the number of wraps you can have when you map from the, let's say from the 2 sphere to the 2 sphere. There are indeterminate ways of wrapping it. Right? You take an orange and you take a towel, and you can either not wrap the towel at all, or you can wrap it once, or you can wrap it twice, etc. Right? So this is, or if you wish, in a mapping from 1 to 1, it's maybe even easier. You have a ring, you have a rubber band, and you can ask the question, how often do I wrap this rubber band around the ring? That's what the homotopy group measures. It measures the equivalence classes of mappings, essentially those which you cannot unwind. And the Versumino terms require that the d plus first homotopy group is an integer, and that's exactly what we use in this consistency condition. Once you've done red minus green, you've wrapped the whole sphere, and thereby what you essentially do is you're mapping. You're now calculating essentially what are the possible wraps that you can have of the sphere. That's why this is actually an integer. It has to be an integer. So the topological reason. Topological in the sense of mathematical differential geometry. Maybe it becomes a little bit clearer if we discuss also the second variant that will appear in this lecture course, which are theta terms. They require, or maybe I should also say one more thing. It's important actually here that the target manifold is simply connected. So I don't have holes in the manifold, otherwise I cannot track this one problem. So there's another condition here that I didn't write down, which is, yeah.
What is the topological term?
What is what?
A topological term.
What it means? So the action contains multiple terms, SH and SWC. And there are terms in the action which are like kinetic term, they're non-topological. But then there are terms in the action which are topological in nature. And an example is this one. It knows about the topology of the. So what I'm trying to summarize, so this chapter tries to answer your question in the sense that I'm giving you some examples of what are topological terms, potential topological terms. But generally speaking, it's terms in your action which know about the space-time. Sorry, both about the space-time topology and about the topology of the manifold wave mapping. So theta terms require a D homotopy group of M B Z. So that would be something like the example in the exercises is a mapping from a ring to a ring. And that is this. So you have a space-time. In this case, it's just time, which is a ring, similar to here. And the target manifold is also a ring. And then you can just ask the question: how often does my field wind? Yes, for example, this is just a mapping from a ring to a ring. So it could be, for example, that this is time, space-time, or time. It could be that you sort of map out this and then you go back. But then that's nothing topological has happened. The other thing that could happen is that you start here and then you go around here and come back here. And that would be a topological configuration. And what the theta term does, it essentially measures exactly this. So as theta has this form, I theta, and then n of little n. And this n just measures the winding number. Winding number. The winding number is shown here. Maybe so I can measure the winding on the ring. And the theta a priori has no quantization condition. This is just what it gives you is it gives the different. So when you have a certain, what you have to do in a path integral, what you do is you're calculating your partition sum by summing or actually integrating over all field configurations. And you give them a certain Boltzmann weight, which is essentially this, how much energy it costs because of this. Right? And then there's quantum mechanics entering here, this I quantum mechanics, there's also an H bar that's expressed. And this tells you about sort of the phase, which you find, the very phase. Here, this here is also something like quantum mechanical interference phenomena. It measures, it gives a different phase, e to the I theta, to different sectors with different winding number. So for example, the sector where I have no total winding, this thing doesn't contribute at all, it comes with a 1. If I have 1 wrapping, then it comes with e to the I theta, etc. And that might actually lead to a destructive interference of different topological sectors. Okay, that's essentially what it is. So this theta is not quantized. Theta is not quantized. So you see the color coding. In the case of the Lesomino term, This here is a function of this n and can be written as an integral. And it's not quantized, but the k is quantized because of topological reasons. Here it's the reverse. This n here, I didn't write it out, but this n, you will see an example tomorrow, where this n can be written out as an integral. This one is quantized, but the tree factor is not quantized. So it's sort of the reverse. Then there's a third situation, which I'm not going to speak about, just I mentioned it. There's also Z2 theta terms. And essentially, in this case, both are quantized. It's at least one way of seeing it. Pasha might speak about those Z2 terms. I don't know. They do appear in the context of topological instead. Okay, so that's it. Today we've derived this first field theory, which is nothing but describing a spin, and tomorrow we are discussing a spin chain.